Yeah, welcome back, everybody. Can you see my iPad?
Yes.
Hope you can. And just as a small startup comment, my name is written the Scandinavian way with 2 A's in it. Not the English way. Okay, so yesterday we talked about formalism for numerical relativity, how to turn general relativity into equations that I can actually put on computers. Today's main focus will be on the algorithms actually in use to solve those equations. And when I usually give talks about numerical relativity, about my work, there tends to be only space for 1 or 2 slides where I say spectral methods and a few more buzzwords, but nothing else. And so for another summer school 2 years back, I actually developed this set of notes that actually explains 3 of the most important numerical algorithms in quite some detail. I hope in enough detail in order then to follow along for you guys. And also do an exercise sheet that Ajith either already has distributed or will distribute, that asks you to implement the 3 methods and solve a very simple evolution equation with them. Okay, but before getting there, let me first continue with a little bit more detail on hyperbolicity and boundary conditions and similar topics that was brought up yesterday as well. As a very simple intro reminder, elliptic equations are just equations of space. The prototypical example is the Poisson equation, or more generally, you can have any type of second-order differential operator as long as your coefficient matrix A is positive definite. The intermediate type I didn't get into yesterday at all, and won't either, are parabolic equations, where you have first time derivatives and second space derivatives, with the heat equation being the most typical example for this type of equation. It doesn't really show up in GR because parabolic equations have infinite propagation speeds, and as such, they are inconsistent with light cones. They show up, however, when one is in apparent horizon finding. And then, of course, the big thing, hyperbolic equations, which is the topic for today, essentially nearly completely. And with the prototypical example being the wave equation, second space, second time equations, or more generally, hyperbolic equations are most easily written down and analyzed in their first order form, where you have a vector of variables, u alpha, can be one variable, can be many variables, both is possible. And then you have the time derivatives of your u alpha, and you have any possible combination of first spatial derivatives. So the different variables of course, will be coupled, which is indicated by the sum over beta here. And you can have different coefficient matrices A for different spatial directions K, which is indicated by the K index on this generic coefficient matrix A alpha beta K. And getting from second order to first order is typically a fairly straightforward way. And for instance, the way this would work for the scalar wave equation is, I've written down the wave equation again here in the corner, in case you forget about it, is to introduce new variables. Specifically, one introduces one new vectorial variable that corresponds to the gradient derivative of psi, and one introduces one variable that corresponds to the time derivative of psi. And using these two new variables, the wave equation itself ends up as this middle equation here, which is now written as the first time derivative on pi, where pi is the time derivative of psi, so this is the second time derivative of psi. And the Laplacian has now turned into a first order gradient terms of this intermediate variable phi, which are the first derivatives of psi. So, of course, if we introduce new variables, we also need new equations for those variables. The simple one is the new equation for, well, we have one equation for pi now, which was the original wave equation. Another quite simple equation is that what's now is becoming the equation for psi, and that is simply the definition of pi. If pi is the first time derivative of psi, well then by definition, the first time derivative of psi must equal pi. And the final set of equation for the phi's, that one is derived by commutation of derivatives. So you take the second equation and you compute its gradient, the gradient of pi. Well, plugging in the definition of pi, this is the gradient of dt of psi, commuting derivatives d by dt of di of psi, and di of psi equals phi. So this equals, at the end of the day, d by dt of phi. Completing the set of equations we need in this first order reduction of the scalar wave equation. So what we now have is 5 evolved variables, psi and pi as scalars, and phi I as a vectorial quantity. And the equation written up here in the top right-hand side of the screen right now are precisely of the form of the generic first order form, with the A matrices being remarkably simple, consisting nearly completely out of zeros, except for the gradient of phi terms in the middle equation, which turn into Kronecker deltas down here. And I'm somewhat confused, which must be a typo in my equations, because there's also the gradient of pi term up here that should be written down somewhere, and I don't see it yet in the equation. D by dt of phi is the last 3 sets of equations. They should be coupled to pi, which is the second equation. So I would imagine that there is No, sorry. The entries in the equation that I actually spelled out in my notes are precisely the d by dt of pi terms. What's missing is in the pi equation, I think, the gradient of phi term. So somewhere there should be one more term in this matrix, which apparently in my notes is missing. And I'm not capable of working out right here live in front of you. So scalar wave has some simple looking set of equations at the end of the day in this general form with coefficient matrices A that are mostly consisting out of zeros and that still have a typo somewhere in my notes here. If you have this first order form, from it follows a notion of characteristic modes and characteristic speeds. And the argument for that goes back to the fact that the local properties of the solution are determined, are probed by the short wavelengths. Therefore, one way to arrive at the characteristic modes is to take plane waves, like the ones written down here, and then in a few lines down, take the high frequency limit, the short wavelength limit of these plane waves. Plane wave is a plane wave. You can write it as with a wave vector dotted into x, but you can also factor out the magnitude of the wave vector. And then what remains as the inner product is a unit vector n hat dotted into x. And you could then rewrite the time term as a v times t, because the velocity is omega over k, the phase speed. And so now we want to look at a given position, x and t, and for a given propagation direction, we want to look at the high frequency limit. So here's our first order equation. We substitute in the wave equation. In the time derivative term, minus ikv comes down from the time derivative. In the spatial gradient terms, a ik n hat comes down because of the eik n x and the x derivative. And now you can take this and you can divide by ik. That turns the first term into a v times u0 alpha, where the u0 alpha is the coefficient matrix of our plane wave. And the second term, what is left is the A matrices contracted with the unit normal n hat of the propagation direction of the gravitational waves. And by dividing by ik, the ik shows up on the right-hand side, multiplying whatever else is there. And if we now take the limit of k goes to infinity, that right-hand side will disappear. So consistent high-frequency plane wave solutions must satisfy whatever is left. And whatever is left takes the form given on the next line, which is an eigenvalue equation, where the coefficient matrices u alpha 0 of the plane wave solutions are eigenvalues of this P matrix, P alpha beta, which is the contraction of the A matrices with the propagation direction. And this eigenvalue problem will teach us what the shapes of the fundamental traveling modes are. That will be these coefficient vectors u0 beta, u0 alpha. And it will also tell us what the speed is of each mode, how quickly it propagates through the eigenvalue v, here in this eigenvalue equation. So, now we have an eigenvalue problem, and whether and how one can find solution will depend a lot on the properties of the principal symbol P. If P is symmetric, or if it's symmetrizable for all values of n, then we always have a full complement of linearly independent eigenvectors with real eigenvalues v alpha. Here, unfortunately, I have a overload of notation. I'm using n for the unit vector, and I also happen to have used n in the nodes for the number of fields. Apologies for that. So in this case, if we have a complete set of eigenvectors and eigenvalues, we can do a complete decomposition of any solution in terms of oscillatory and traveling modes. And so we can represent the entire solution in fundamental modes. If P is symmetric or symmetrizable, this whole thing is called symmetric hyperbolic. If P of n is not symmetric or symmetrizable, but if it still has a complete set of eigenvectors and real eigenvalues, then the properties are just mentioned, but it will be more work to construct the eigenbasis. So it's a little bit harder to do, but everything still works out. And this goes under the name of strongly hyperbolic. If P of n has real eigenvalues, but not a complete set, no complete set, then the equations are called weakly hyperbolic. And well, if P of n doesn't even have real eigenvalues, if some of them are complex, well then life is even worse. I don't even know what the name then is, because those complex eigenvalues would not be traveling waves, but exponentially growing waves. The rub in all of this is that for symmetric or strongly hyperbolic systems, those are well posed. And weakly hyperbolic systems are not well posed. And this is why this analysis in hyperbolicity is so important. It gives a handle on when equations are well posed, when they can be solved easily or realistically. Well posed means that the equations have a solution exists, the solution is unique, and the solution depends continuously on the initial data. The continuous dependence on the initial data is important because you want that a small change in initial data, because of measurement uncertainties, for instance, will only lead to a small change in the subsequent evolved solution. However, in math speak, depends continuously is actually a fairly weak statement. It basically is equivalent to saying that the norm of the evolved field as a function of time of the solution must be bounded at most by an exponentially growing function of time times the initial norm. So, what happens when you have non-hyperbolic systems? How can things go wrong? Here's the simplest weakly hyperbolic system that I am aware of. It's two equations, the time derivative of u1 plus the gradient of u2 equals 0. The second equation is the time derivative of u2 is 0. Looks perfectly reasonably and fine. You can write it's in 1 plus 1 dimension, so there's only one matrix for the derivatives. The eigenvalues both are 0, but there's only one eigenvector, 0, 1. We don't have a complete set of eigenvectors here. So that's weakly hyperbolic. And the next few lines tell you how things can go on. Consider the initial conditions u1 identically 0 and u2 equal to a oscillatory solution with some small amplitude epsilon. Well, obviously the initial norm is of order epsilon. u2 of order epsilon is the only thing that's non-zero. However, if you now look how u1 develops as a function of time, its time derivative is u2 prime. That has a factor k coming in. And so u2, the norm of u as a function of time, will grow proportional to epsilon times k times t. And if one chooses an arbitrarily large k, arbitrarily short wavelengths, the solution is bound to blow up ever more quickly. And that's precisely what happens typically if you try to evolve numerically weakly hyperbolic systems, that short wavelength modes of the underlying analytic system of equations blow up quickly, ever more quickly the shorter the wavelength gets. But in your discretized equations, you have a certain shortest wavelength mode that you can represent. As you increase resolution, the shortest mode that's represented becomes smaller and smaller, and causing ever quicker blow up of the solutions. You won't be able to find convergence in those problems. And as I said, the ADM equations are only weakly hyperbolic, and realizing that it was a problem was one of the major accomplishments in the 1970s and 80s and 90s. If you now look at the scalar wave, playing this game is fairly straightforward, and you can even kind of do it by trial and error. You have a certain principal part, principal symbol, which I don't really believe anymore because it strikes me there's a term missing. However, you can now plug in, essentially by trial and error, the mode 1, 0, 0 gives you identically 0. The mode 0, 0, be orthogonal I, where be orthogonal I must be orthogonal to n, also gives you 0. And then you have two other modes, one in the middle component and plus minus n in the phi components. And they have speeds of plus minus c. And then again, they reproduce themselves as eigenvalues should. So we have 5 modes. 3 of them are zero speed fields, psi itself, and the phi orthogonal. The gradients of the phi of psi orthogonal to the propagation direction. And there's one speed moving at the velocity of plus c, and one field propagating at a velocity of minus c. There are certain combinations of the evolved variables. By the way, these evolved variables show up precisely if you look at the standard solution of the scalar wave equation 1 plus 1d. The solution is a generically shaped left-moving mode, given here by the function f, plus a generic shaped right-moving mode, given by the function g. where the left and the right moving parts come up by how the f and the g functions depend on x and t. The one has the argument x plus ct, the other the argument x minus ct. If you now evaluate for this generic solution psi, the two modes I was just spelling out for you, well, calculation isn't particularly long. The important part is that one of the two modes condenses down to being essentially f. So the u minus, the left moving characteristic mode, is f, or the derivative of f. And u plus turns out to give you the right moving mode, g. So the characteristic modes do represent and do reproduce simpler results in lower dimensions. This now motivates how these modes are used when setting boundary conditions. Say you have your scalar wave here, but you only want to solve it for negative x values with a boundary condition at some, say at x equals 0. In that case, from the simple form of the two traveling modes, you would already expect that G is the right traveling mode that is going to leave the computational domain. So it shouldn't be constrained, it should just be allowed to leave. But F is the incoming mode, and so as more and more of the F shape is entering the computational domain, you're going to need to supply what the next part of the F shape is that is going to enter your computational domain. So basically what this means is, in this 1+1 example, what you should be doing is you need a boundary condition for F, but you don't need a boundary condition for G. And in the more generic way of playing this game, U minus is the left moving mode. It's the mode that has a negative velocity relative to the unit normal m. It's left traveling, it's entering the computational domain, and one must apply a boundary condition to that mode. U plus, in contrast, is right traveling, it's leaving the computational domain, and you must not apply a boundary condition on U plus. So this is how hyperbolicity and the decomposition in characteristic modes can teach you what type of boundary conditions to apply. Okay, so that was what I wanted to say in terms of more recap of theory of partial differential equations. And now I would be switching over to numerics. But before doing so, let me ask whether there's any questions so far. Okay, then let's move on and actually begin talking about numerical solution of PDEs. I've written down again as introduction a hyperbolic PDE in first order. The only difference I have here compared with earlier is that I have written the derivative terms in the middle in what's called a flux form. So instead of a coefficient times the gradient of the fields, this is now the gradient of a function of the fields. And in many, many important cases, the two versions are completely equivalent. Well, you can always go from the flux form to the other form, essentially by a mere coordinate, by mere application of the chain rule. That's df du times du dx, for instance. So you can always go from the flux form to the more generic form, but for many, many systems of interest to us, they can also always be put in the flux form as well. So that there isn't really that much generality lost so far. In what follows below, I sometimes use the flux form, I sometimes use the other form. And now that to do numerical analysis, there are two big questions that need answering, and where one needs to make choices in how to proceed. The first question is, one needs to approximate the continuous solution u of x and t, which has infinite number of degrees of freedom, by some approximated version uh of x and d, which only has a finite number of degrees of freedom. There are many different choices how to do this approximation, and this basically is one of the dividing lines for the different methods I'm going to discuss later in this lecture. Second, now that we have some approximate solution with a finite number of degrees of freedom, uh of x and t, in what sense does this approximation still satisfy the original PDE? Because we have approximated the solution, thrown away a large number of degrees of freedom, we won't be able to satisfy the original PDE with absolutely. We will have to make some approximation there as well. So let's look at how three different methods are actually addressing these questions and what happens then. In my numerical examples, I'm even going more simple than the flux conservative form. I literally go down to the one-dimensional advection equation, d by dt of u plus d by dx of u equals 0, with u being a function of x and t. So this is just the solution here is a constant shape. You can pick whatever shape you want as your initial condition, and that shape just translates with uniform velocity to the right. The easiest way and most widely known way of discretizing solutions or equations is with finite differences. So you take your x-axis and you put down a set of grid points at equal distances. I'm doing equal distances, you can also do unequal distances. So you have a finite number of x's, x0 to x, whatever capital N is, however many you have. And they have a grid spacing h, which is the difference between neighboring grid points. By the way, it's the convention that h is used as the grid spacing that also comes up in the name for the discretized solution UH I had on my previous slide. And so you're representing the solution at discrete spatial points, and also in this very simple first example, also at discrete time points with time spacing delta t. And so our function of on R2 with infinitely many degrees of freedom becomes a function at a discrete grid of grid points. Now we have this discrete representation of our original function. Now the question is, how can one deal with representing the PDE appropriately? And as the name suggests, the way to do this is by approximating the full time derivatives and the full spatial derivatives by the appropriate finite difference versions of at the grid point values. For instance, the time derivative could be written as u at a certain x grid point at the next time step minus the current time step divided by delta t. Spatially, the same is true. If you want the spatial derivative at a point xi, well, you can evaluate the function one grid point to the left, to the right, I'm sorry, one grid point to the left, and you take the derivative and make a finite difference derivative, and that way get an approximation for d by dx. Taking these two expressions and plugging them into your these types of expressions are arrived at by Taylor expanding. For instance, if you have u plus t plus delta t, you can write this as u of t plus delta t times u dot plus 1/2 delta t squared u double dot and so forth. And you truncate this at whatever appropriate order you want to truncate. And you can then solve for one of the terms and arrive at the finite difference representations. For the spatial one, there's a little bit difference because I was actually changing back and forth. So one way of getting at the spatial thing is you Taylor expand u plus x, u of x plus h, u prime of x plus 1/2 h squared, u double prime of x, and so forth. And you Taylor expand u minus x, x minus h, where you're getting a minus h, u prime, and so forth. The nice thing by doing it symmetrically, if you now subtract these two expressions from each other, you end up with ux plus h minus ux minus h. You get the term you want here from the first order terms in the middle. But the nice thing is that the next higher terms, because you were doing this symmetrically, the plus 1/2 h squared, the plus 1/2 h squared are actually falling out and cancel each other. So in this central derivative formula, you actually cancel the second order term. And what comes out of it is you have a formula that gives you the derivative of u that is accurate with an error that goes down like the grid spacing squared. In contrast, for time further up, I used one-sided finite differencing, the future time minus the current time, and therefore I'm getting a larger error for the time difference of order delta t. So just some background of how these finite difference stencils can be computed. If I'm now plugging my approximations into the original evolution equation, well, I'm getting this type of equation here, the time derivative on the left-hand side, the spatial derivative on the right-hand side. And I have no idea why my notes don't have the factor 2 sitting here. It should be here, I think. And now you can use these equations and solve for u at the new time. And you get u at the new time equals some function of the u's at the current time. It starts out with u at the same grid point at the current time, and then there are terms that contain u at the grid point to the right and u at the grid point to the left. So schematically, you have data at a time series at the time step tk, and now in order to compute the data at the next time, you are using information from 3 grid points before and combine this together to get the data at the one data point at the next point. You can do the same for another data point. Again, you're computing over, in this particular scheme, you would be combining 3 values from the previous time step to get one value at the new time step. The nice thing here in this scheme, and in all the other schemes I'm talking about today, is that this scheme is explicit. That means there's always a simple equation that can be directly evaluated that gives us each one of the new terms. We do not have systems of equations to invert. if you discretize elliptic equations, for instance, the fact that elliptic equations have boundary conditions everywhere and have to be solved all in one will then result in big linear systems of equations that must be solved. And that's a topic I won't get into today. Similarly, there are so-called implicit evolution algorithms where one again has to solve systems of linear equations at the next time step to get all the solutions. So the nice thing about explicit algorithms is they are really simple and you can very easily write them down and code them. One of the nasty things is that they come with a courant limit. Essentially, the time step has to be smaller than, roughly speaking, 1 over speed times the spatial step size. Intuitively, you can understand this type of limit by that if you're trying to take a time step that is too large, say from T1, really large time step to T2, and you have a fairly fine grid spacing, if you have modes that, if you're now only taking these 3 time steps here to compute the new time step up here, you can run into issues with the propagation of information. If the velocity in your equations is too large, if you have information propagation because of large velocities that couple a time step further away, at a grid point further away with the grid point you're computing, well, then in that case, your original grid points in the middle cannot be enough to find the solution up here because they don't respect the information propagation in your solution. So far the method I was describing to you is limited by the fact that the time step treatment is very simplistic and we are only getting we have a very large time stepping error of order delta t. Let me introduce you to the generic trick of fixing this and dealing with time in a rather flexible manner. This is called the method of lines. The idea here is to discretize space first, and only space, and keep time continuous. In this particular case, the left-hand side of the advection equation has still a partial derivative with respect to time. However, evaluated at the discrete grid points only. And the right-hand side is already discretized, the spatial derivative, into a finite difference stencil. And now the viewpoint of the method of lines is to consider the set of views at the grid points as a vector of variables, a vector of real numbers, and then to write the evolution equation in this form here as a time derivative of acting on the vector of numbers is equal some right-hand side, where the right-hand side is just whatever I have spelled out above. So the f of u is some vector-valued function, and in this viewpoint, the equation double star here is now a system of coupled ordinary differential equations. We have gotten rid of the partial differential equations, and we have now a set of ordinary differential equations. And those we can now solve with any time step of ordinary differential equations one might have. For instance, the good old forward Euler method, where you're saying the solution at the new time step is the old solution plus delta t times the derivative. Schematically, this corresponds to here now for change time goes right, I apologize, and the solution u goes up. And so at time k, you're at a certain point here. And the right-hand side of your equation, the f, gives you the slope. So it gives you a direction in which to go in this ut space. And in forward Euler, you take the slope and you go linearly along the instantaneous slope until you reach your next time step. This is good for a single time step of order delta t squared. If you evolve to some total time t, you will have to do capital T over delta t time steps. Each one accumulates an error delta t squared. And so in total, you get an error of order delta t. Forward Euler is what's called a first order accurate time stepper. And by the way, the first discretization scheme I introduced to you above boils down to being exactly forward Euler. So one example about this, as I said, we're still solving the advection equation. Nothing has changed. I'm picking as the initial condition this interestingly looking function, e to the minus 2 cosine 2 pi x. I wanted something periodic because periodic boundary conditions are much easier to implement than anything else. But I wanted something that's not just a cosine, because it would have been too easy for the spectral methods that come later. And no big surprise, here's the initial solution in blue, time 0. And as you evolve from time 0 to 0.1 to 0.2, the solution moves to the right. And it eventually exits on the right-hand side, but since the periodic boundary condition, it comes back in from the left. And at 0.7, the solution is here, the red curve, almost back to its original shape. If you have solved this with finite difference solutions, here's one example of how this is going to look like. I'm sorry for changing the color scheme here. At time 0, you have your initial data, and as the thing evolves, well, you're going right and right and right. So the solution propagates to the right. And what I've also spelled out here is the solution after one full light travel time at time t equals 1. At that point, you should be back to your original solution. However, what you see here is that the solution actually looks already significantly different from before. And this has two reasons. This is actually three reasons why this happens. One reason is that I'm using very primitive methods with only first order time steps. The second is that I'm using fairly low resolution. I only have 40 grid points in this particular example. And the third reason why this is happening is that this is generally happening in finite difference methods, that finite difference methods are not good at vecting solutions. Typically, different modes on your finite difference grid advect with slightly different speeds, and so the shape that actually should be constant as it's being evolving is changing as the different components of this shape are numerically moving with ever so slightly different speeds. For the near term, there's no big deal here in fixing these problems. And the way to fix them is basically to increase numerical resolution. And this is what happens in the second plot I have down here on this slide now. This is now what's called a convergence test, which is pretty much the most important thing the most important tool to make sure numerical codes behave the way they would. What I have done here is I have evolved in the Euler, the advection equation on a wide variety of different grids, going from 20 grid points up to 640 grid points, and with a wide variety of different time steps, delta t. And so what you're going to see here is a few important features. So let's try and interpret this graph. First of all, note that the solution I was showing you above corresponds to this point here. It has n equals 40, it's the orange curve, and it has a certain time step. I didn't tell you what time step it was, but it corresponds to this point here. If I now were to run this with ever bigger time steps, then I end up with these 2 points here on the orange curve, where the error becomes exceedingly large. So the y-axis on this plot is the L2 error of the solution, where this point here is roughly 1. And so the top end here is 2 to the 7, which is quite a bit. So if I had to evolve this with larger time steps, the solution would be blowing up. This is precisely the representation of the Courant limit, that with large enough time steps, your code will blow up if you have explicit time steppers. And the plot I was making here is basically the worst you can get away with. If you now keep the spatial resolution fixed at 40 and you go to smaller and smaller time steps, at some point, the error you have in your solution becomes independent of the time step. At that point, the time discretization error becomes so small that it's no longer important, but the spatial discretization error is still there, and after one light crossing time, gives me an error of a quarter. If I want to have this error smaller, I need to increase the number of grid points, say from 40 to 80. And if I now go to 80, I'm actually gaining a factor of 4. In accuracy to 160, I'm gaining another factor of 4. To 320, I'm gaining another factor of 4. So I have gained 1, 2, 3, 2 to the 6. I went from 2 to the minus 2 to 2 to the minus 8. But not only do you need more and more grid points, but also, and this decay here, by the way, this decay here, by factors of 2 to the 2 each time, is precisely what you would expect and what one needs to check for the second order spatial convergence. However, because the time is only first order convergent, you also have to go to smaller and smaller time steps in order to realize the higher accuracy. So if you want an accuracy of 10 to the minus 8, well, you can get it with 320 grid points, but only if you pick a grid space at delta t that is as little as 10 to the minus 5. So you're going to need not only many grid points, but with this low order time discretization error, excessively small grid time steps. Well, the time discretization error can be improved quite easily because we have this nice decoupling of space and time. You can use Wange-Kutta 2 where one starts out at some initial point over here. One first computes a slope W1. One goes half a time step along this slope W1 to get an intermediate point at time t k plus 1/2. At this intermediate point, you're evaluating your right-hand side again of getting a new slope. And using this new slope, this W2 slope, you're now transposing this down to your original step, and you're taking the full step with this new slope. Indicated here by the double uk plus 1 equals uk plus the new slope W2 times delta t. If you do this, you end up with a second order scheme where each time step has an order delta t cubed. You can repeat this with the really famous Ronge-Kutta-4 method, where you're doing four function evaluations with 3 intermediate slopes. And at the end of the day, you're combining all the 4 different slopes in a smart way together to get your new time step to order delta t to the 5th. So there's quite a few more of these simple looking time steppers around that give you better results. And now we are actually somewhere in terms of improving our convergence test. So here's the same convergence test as before. Earlier on, we were focusing on the case with 320 grid points. For a first order time stepper, you only got somewhere with time steps of 10 to the minus 5. But now we can reach the error 10 to the minus 8 with 320 grid points and time steps of order 10 to the minus 3. Or with Ronge-Kutta-4, we still get the same delta t error 10 to the minus 2 to the minus 8 with time steps approaching 10 to the minus 2. So we have gained a lot in being able using larger time steps already when solving the equations. Here, by the way, you're seeing a different feature. The biggest time steps I'm plotting here are always equal to the spatial grid size. So that corresponds to a Courant factor of 1. For Ronge-Kutta-2, these biggest time steps look fishy and eventually blow up if you're going to high enough resolution. So the actual Courant limit for Ronge-Kutta-2 is a little bit below Courant factor of 1. For Ronge-Kutta-4, all looks perfectly fine all the way to the end. And so as it happens, Ronge-Kutta-4 is capable of taking slightly bigger time steps without messing up anything along the way. Another advantage of taking Ronge-Kutta-4, and another reason why Ronge-Kutta-4 is so popular, it's really simple and it allows fairly big time step and it's fairly accurate. However, if you begin reading the literature, there's also a lot of other cool stuff around. And in the spec collaboration, our favorite time stepper goes under the name of Dormant Prince 853. It's an 8th order method, so the time stepping error will go down as delta t to the 8th. Unfortunately, it needs 13 function evaluations, so it's more expensive than 1 function evaluation per order. However, now come the cool stuff. The same 13 function evaluations, W1 to W13, can also be combined to give you a 3rd order and a 5th order accurate time step. you can use these to compute error estimates, how accurate your time-stepping error actually is, and using these error estimates to do adaptive time-step choices. So you basically tell your code, I want an error of 10 to the minus 4, and it uses the third and the fifth order time-stepping formulas to estimate the actual time-step error, and then choose a delta t so big as possible to still give you the error you are asking for. This typically leads to very large time steps, and this method has a much larger Courant stability limit than the other ones, so you can take very large time steps. And you typically end up taking time steps that are larger than where you want the data. And there comes another cool feature of Dormant Prince. It has what is called an embedded interpolation formula. So, taking the 13 function evaluations you already have and 3 extra ones, you can then combine these 16 function evaluations such that you can get U at any continuous time within the time step with high precision. So you're doing time interpolation at very little extra cost. Oh, and finally, W13, the last one you computed in your previous time step, happens to be the very first function evaluation of the next one. So it's not 13, but it's only 12 function evaluations on average per time step. So there's very cool ODE solvers around. You should definitely be aware of Runge-Kutta 4, but you should also be aware that there's a lot more nicer things around, like this Dormant Prince 853, which actually isn't even that sophisticated. You can find it, for instance, in numerical recipes. Okay, on this slide of convergence tests, I also have our next method listed here. And this next method, let me just compare it to Runge-Kutta 4 and our second order finite difference code. This next method gives us, and let me get rid of all these colors here. And let me remind you that the finite difference code had an error of 2 to the minus 10, which is roughly 10 to the minus 3, with 640 time steps, spatial grid points. This next method I'm going to talk about gets to the same 10 to the minus 3 with 12 grid points instead of 640. And even more so, as you increase the number of grid points, not multiplied by a factor, but by adding a certain number of extra grid points, you are decreasing your accuracy by orders of magnitude. And so, for instance, by going from 12 points to 24 points, the error went from 10 to the minus 3 to 10 to the minus 9. If I wanted to go down to that error with the really simplistic finite difference code, well, each factor of 4 doubles the number of grid points. I have here, I think this needs 2 to the 8. This would need about 1,000 times more grid points. I'm at 640,000 grid points. So, this method here that looks so astoundingly more accurate than the finite difference code is one of the pseudo-spectral methods, or is a pseudo-spectral method. And so let's actually talk about what this is and how it comes in. One motivation into spectral methods is to note that so far our spatial discretization, the choice of grid points, was completely ad hoc. We just decided, equal spacing is good, let's just use it. We did not address the question whether there's better choices for grid points around. And it turns out there are better choices. And this leads to the spectral methods. But before going to grid point choices, let's just consider Fourier series first. So let's take a u of x, where x goes from minus pi to pi, and let's try to expand u as a discrete Fourier series. It's discrete because our interval is of finite size. The coefficients can be computed by an integral of u of x times e to the minus I n x. And now the big trick is one can integrate by parts. We find a first term here, I over n u of x e to the minus I n x from minus pi to pi. And we find the integrated by part version left over, where we now have one extra derivative on the u function. The important thing when doing this is that if u is periodic, then the boundary term, which has u of pi minus u of minus pi, is identically zeroed. Let's integrate by part. We get again a boundary term that now has u prime of pi minus u prime of minus pi. And if u prime is periodic, this boundary term vanishes, and we get whatever is left over. The important thing to note here is the coefficients of what's left over. 1 over n, 1 over n squared, and with each more integration by part, one is picking up yet higher orders of 1 over n. So, after k integrations by parts, we will have that the Cn coefficient as a function of n will be decaying like 1 over n to the k, at least. And this is valid for all k, and that means that the Cn decay exponentially n. So, spectral methods, wrong button. This looks awful because I had erased out some scribbly text on my notes after scanning them in. The point here is that if you expand periodic functions in a Fourier series, then you get, with very, very few basis functions, you can get very, very high accuracy. And that means the truncated Fourier series will be very accurate. And so this is the underlying idea of spectral methods, that one expands in suitably smart basis functions to gain from this exponential convergence. So how do you actually do this in practice? You choose a uniform grid. And I'm just seeing a question about how they compare in speed. I'll address this when I'm done with the spectral methods. For periodic problems, you still choose a uniform grid. This hasn't changed. It is uniform because periodic problems are translation invariant, so there is nothing better. And now the trick comes. that in order to compute the spectral coefficients of your Fourier series, it is precisely an integral. However, this integral turns into, using a Gaussian quadrature formula, turns into a sum at the grid points. And this sum at the grid points for periodic problems turns out to be a fast Fourier transform. Once you have the coefficients, you can compute the derivative, well, by taking the derivative of your series. E to the in x d by dx gives you an extra in. And so the series has the same form as before, with new coefficients Cn prime. And the Cn prime have a simple relation to the original spectral coefficients. And then you do the inverse Fourier transform, and you get the derivative of u at the grid points. So practically, to do this for the advection equation, you do the method of lines exactly as in FD. But whenever derivatives are needed, you don't use the finite differencing derivative, spatial derivative, but you use this block here that computes derivatives by pseudo-spectral methods. And that this leads then to these astonishing convergence that I have shown you up here for the smooth problems. So one question was about computational cost. Spectral methods are more expensive because you have more operations per grid point per degree of freedom. For instance, you have these Fourier transforms and inverse Fourier transforms. But this cost is generally compensated for quite easily by the much lower number of degrees of freedom. And because of the higher convergence rate, the more accurate a solution you desire, the more advantages are the spectral methods in terms of computational cost. In this particular example, I would already imagine that the n=12 spectral method is on my laptop at least 10 times faster than the n=640 finite difference code. And as you go further down and the 600 grid points become 500,000 grid points, the speed advantage just increases ever more. In more complicated problems, of course, the speed up advantage is not as bad, but still I say even in numerical relativity, the spec code does quite well compared to other codes. So far for periodic problems. And what do you do for non-periodic domains? Say -1 to 1. If you don't have periodicity, then the Fourier series isn't the right thing to do. What one should do instead is use polynomials that are adopted to non-periodic domains. In particular, Chebyshev polynomials are very favored. They are, because of their quite simple forms with causes and arc causes, they still allow a Fourier series to go to the spectral coefficients. And so you can still very efficiently go from the real grid points to the spectral coefficients and back. One can also use Legendre polynomials, which I will come to later on as well. They have similarly fast convergence to Chebyshev. The one disadvantage is to get to the spectral coefficients, you have to do a matrix multiplication. But as long as your order is small enough, it doesn't really matter. One downside of the spectral methods is when your data becomes non-smooth. If your function u is only ck, then the integration by part argument breaks at some point because boundary terms are going to be left over. And that then limits your convergence of your coefficients to being algebraically rather than exponentially. This would, for instance, happen at the center of black holes in the moving puncture approach. And that is one of the reasons why, for binary black hole, SPEC actually uses black hole excision. And so what we do in SPEC in practice is we have two black holes, say, sitting down here. Around them, we first have concentric spherical shells. And then we have cylinders and other interesting looking domains that are still simple enough that you can expand in spectral basis functions. And ultimately, there is, at large distances, a set of concentric spherical shells again. Here's the whole thing in actual nice visualized images. If you're zooming in, you see a big black hole and a little black hole, where the little black hole is already very deformed, with the various domains at intermediate distances covering the space in between. And up here at large separations, this is now where the spherical shells start, and there's a set of concentric spherical shells that go to large outer radii. The nice thing about these concentric outer radial shells, for instance, is gravitational radiation has very low L angular structure. So all these outer spherical shells have a very low angular resolution. And if you want to move the outer boundary further away, you do so by keeping L constant and only putting more radial shells there. And so the cost is only linear in distance to the outer boundary. Recently, yet a different scheme has really come into favor in numerical relativity. It goes under the name of discontinuous Galerkin methods. Luciano Rizzola is working on this, Bernd Brüggemann, the MySXX collaboration, Kao et al., Eric Schnetter. It somehow feels like everybody suddenly is keen on doing discontinuous Galerkin. However, there's no full compact binary coalescence code yet demonstrated that works and works well with discontinuous Galerkin. Nevertheless, I, like so many others, believe this is the future. And so in my last 20 minutes, I will try to give you a brief flavor of why discontinuous Galerkin is so highly regarded these days. So the idea of discontinuous Galerkin is to fill the volume with elements. Those could be big elements like this one here. Those could be smaller elements like these here, or even smaller like those over here. They are all fundamentally distorted cubes, but you can distort them in such a way that you can also get boundaries that are curved and similar features. In 1D, the elements are basically just sitting next to each other, and even in 1D, they could in principle have different width. In each of these elements, we expand in basis functions. So in element dk, say this element here, we have a local solution uk that is only on this element, that also has the letter h for an approximate solution. And this is a sum in some basis functions on this element. One can now imagine two different types of refinement. One can use what is called H refinement. One can cut elements into pieces, and that way increase capital K, the total number of elements. This is advantageous near shocks, where expansions in basis functions will break down and won't work well because of the discontinuities. So Mier-Schoch's the idea is you do H refinement and you get just many small elements. However, one can also do P refinement. Keep the element as is and increase the expansion order in the element, the nk here, in some elements or all elements. And this you're doing in smooth region, and so you're actually benefiting from the exponential convergence, from the very quick convergence as the order of polynomials is increased. So those are the two basic ideas in discontinuous Galerkin. Here's one example for our traveling wave solution. This is how such a solution would look like if I have 4 elements. My x-axis goes from 0 to 1. It's split into 4 pieces, no big surprise. And in the first panel, in each element, I only expand in linear order basis functions. So in each element, my solution is represented by something that is just a straight line. And it will look something like this. And the word discontinuous comes into discontinuous Galerkin because one is not even forcing the solution to be continuous. It will literally be discontinuous pieces. If I go up to expansion order 2, I have parabolas in each element. And it's already beginning to appear to look like the actual solution being evolved. N equals 3, we have cubic functions. N equals 4, we have 4th order polynomials. And despite only having 4 elements, it's now already very clear that this is turning into a continuous function, which is a good representation of the actual solution. So this is the underlying picture you should have of discontinuous Galerkin. We have separate elements, and in each element we have a separate basis function expansion, UH of k of x equals sum of coefficients, UH k comma I, summing over I, of some basis functions I of x. Okay, the basis functions are flexible. I haven't told you yet what basis function to use, and in principle you could use anything. Legendre polynomials are in very high order, very high regard. Among the nice feature is, as all polynomials, they are orthonormal to each other. They also have their own set of associate collocation points xi, which come from Gauss quadrature formulas. And what this means is, if we want to take an integral like f of r dr, we can do so by summing it at the collocation points ri with some Gauss quadrature weights w. And the point here is that this is exact for polynomials up to a remarkably high order, 2n plus 1. This is important in particular because we will soon make a lot of integrals between the basis functions. If we're working to nth order, the basis functions is an nth order polynomial. And so this Gauss quadrature formula will be exact because it is exact for polynomials of order 2n. So we can actually evaluate the integrals that show up later without making any errors when evaluating the integrals. One step further, one can now switch over to interpolating Lagrange polynomials based on the Legendre collocation grid points. And the Legendre collocation points they are unequally spaced. There's a smaller spacing near boundary, and this smaller spacing near the boundary allows to do interpolation without Gibbs phenomenon. If you look at the interpolating Lagrange polynomials, like here's one that is 1 on this particular grid point and 0 elsewhere, it is well behaved on the set of Lagrange Legendre collocation points, but here the same Lagrange polynomial on a grid with an equal space grid looks fairly good near the point you're interpolating, but then near the boundary it actually overshoots. And this overshoot becomes larger as the order increases. This is the Gibbs phenomenon, yet again. Equal space grid points are bad near boundaries, and the Legendre collocation points fix that. So, where does this leave us now? Here's again the picture we have in mind. We have different domains, and in each domain we have an expansioner, and we need everything being put together. At that point, we need equations for the UK to close the scheme and actually do something. If we have our expansion, as I've written it down here, we can, and our standard PDE, the one we have been looking at, the 1D advection equation, we can evaluate the residual of this function. It basically is the time derivative, and it has all the spatial terms built in. Because we know the solution as series and basis functions, we can evaluate these derivatives without any extra error. And now the trick to get to equations that approximate the original PDE is to require orthogonality of the residual with our basis functions. So if we integrate the residual over a certain element, the residual times the basis function, then we want to have the 0, and this should be true for every basis function on this element. And that gives a set of equations that is as big as the number of degrees of freedom we have. The next step is to integrate by parts. If we take the residual, well, let me see, where is the integration by parts? If we take the residual here, this term, the df dx term, and integrate by parts, what we get is a f dl dx. The derivative has been moved over onto the basis function we are integrating against. And we get a boundary term, which contains the flux times the basis function at the lower and at the upper boundary of the element we are working. The solution is discontinuous still, as I have shown you. So at a boundary, we have the fact that the flux on the left element, the kth element, evaluated at the boundary point, will in general be different from the flux of the next element evaluated on the same boundary. Now, in order to couple the elements, one defines a unique flux at each boundary. This is called F star at the boundary xk. The F star will couple the different elements together. And it will be this F star that will, at the end of the day, cause the solutions to become more and more continuous as the accuracy is increased. You might have noticed this already up here. The size of the discontinuities is getting smaller and smaller as I'm increasing the resolution. And the flux is the piece that's responsible for implementing this. So there's a lot of flexibility in defining these fluxes. And the standard textbooks here, Hesthaven and Warburton, it is also given in the list of books, says very helpful specification of F star, most naturally related to the dynamics of the PDE. Well, yes, I honestly don't really have understood yet the magic of choosing F star in generic cases. I know that for advection equation, something excessively simple is a good choice. For instance, this expression here, you don't need to understand it. It's also given in the problem set that comes along with this action. The trick now is, you standardize on a flux on a boundary, and you substitute it in. This is now called the weak form of the discontinuous Galerkin equations. And the final step is to integrate backwards by parts, shifting the derivative back from the dl on the flux term. And by doing so, one picks up a second boundary term as well. And what is left over on the left-hand side here is essentially the original equation, du dt plus df dx minus g, and every term integrated against each of the basis functions. And that should be 0, but what we have now picked up in this whole process is a right-hand side that is going to implement boundary conditions. Okay, so this all looks really crazy so far. However, what one does now is one substitutes in the actual expansion for the discretized functions. So h on the kth element is a sum over expansion coefficients times basis functions. This term will go in here into the time derivative term, and it will show up as a time derivative of the coefficient in the next line. We also have the basis function here. That basis function is also going up here, and it will show up as a basis function times the original basis function we have here in the next line. It will show up as integrals of two basis functions against each other. For the f term, let me switch color. For the f term, f is again a series expansion coefficients times basis functions. This one goes in here. This will lead to the coefficients And the derivative is put on the basis functions of the f expansion, and it is still multiplied by the basis function that is already here from the orthogonality of the orthogonality relation. So this is this Lj here. And you can play the same game for the G term, which I have not done. When now the dust settles, what we have is we have these types of inner products of two basis functions against each other. This is going to be called the mass matrix. And we have that mass matrix sitting here, multiplying the vector of time derivatives. We have on the next term inner products of the basis functions with the derivative of the basis functions. This is called the stiffness matrix, and it is the matrix in front of the f, the vector of variables. And for the G term, we again have inner products of two basis functions. We have the mass matrix again. The mass matrix and the S can be pre-computed. They only depend on the basis functions. And if we're now dividing through by the mass matrix, we end up with this set of equations here. The first line is now remarkably simply looking. The time derivative of all the expansion coefficients is a certain matrix, m to the minus 1 times s, times the fluxes plus the g's. And then there is a fairly awful looking second line that enforces boundary conditions. The second line is awful looking, but we are again back in the methods of lines scheme. The big advantages we now have here is the first line, where most of the work goes, is completely d-local. It separates very nicely into block diagonal matrix operations. And the second line is, well, it couples the different elements via the boundary fluxes. And so this is where communication is going to go. And just to show you how well this can work at the end of the day, here's again a convergence test starting out with the example solution I already showed you earlier. And that example solution corresponds to this particular green point here. The x-axis is the number of elements, and the n here is the expansion order in each element. If I only have expansion order 2, I get fairly modest convergence, that is third order in the number of elements. Not too exciting. But as I increase the expansion order in each element, I can make the convergence faster and faster, and then fairly quickly reach round-off limit of my laptop. And so this method works remarkably well and gives the flexibility of choosing how many elements and how high order the elements to have. And it also does so with minimal communication needs between elements. So the method is very good and easy to parallelize. And in some sense, there's also a question in the, so there's a few different questions here, so I'm not sure how many of them I have overlooked in the meantime. Let me just go from the bottom up. How is discontinuous Galerkin different from finite elements in terms of different size of elements? It's quite similar, except that finite elements is typically a lot lower order and requires the elements to be continuous across from one element to the other one. And it's precisely the discontinuity that allows discontinuous Galerkin to reduce the communication needs quite substantially. I don't recall when I didn't pay attention when the question about why does it fail for shocks was asked. Is this question still relevant, or has it been answered in the meantime?
The question about the spectral, why do the spectral methods fail for shocks?
It's simply put because you're losing the exponential convergence. If you have solutions that are not infinitely smooth, the exponential convergence is lost. And that goes back to the fact that the integration by part argument will no longer go through. And so you will end up at a certain order. Say, if you have a C2 function, then you will end up with this particular boundary term here that goes like 1 over n squared. And at that point, the size of the spectral coefficients only decays like 1 over n squared and no longer exponentially. And one would need many grid points, and then the extra cost of the spectral method would be useful anymore. And this was also, by the way, the end of what I had prepared. I think I have touched on this already. There is an exercise sheet that goes along with this lecture to enforce the concepts, teaching you to actually code 3 different methods for the advection equation. Do we have any further questions? Then, thank you very much for your attention.
Thank you very much, Harald, and we'll see you tomorrow. Thank you all, and see you tomorrow. Bye.